This video goes over some examples of non-linear regression. So up until this point, we've been looking at positive correlation, no correlation, and negative correlation. All of the ones that we've looked at so far have shown linear relationships. So in other words, the best way to fit the data is by using a line. And so we can draw a line of best fit. Most of the relationships that we study in the real world don't follow linear patterns. And in these situations, it doesn't make sense to draw a line of best fit, but rather to use a non-linear regression and draw a curve of best fit. The curve could take the form of a variety of different functions, and there are a few listed for you here: quadratic and exponential, which you should be familiar with from previous math courses. We have two coefficients to describe correlation in data. The first one that we've looked at is R, or little r here. This is the correlation coefficient. This is only for linear relationships. For non-linear relationships, we look at R squared, which, if you remember, is the percentage changed caused by a particular variable. And R squared applies to any type of regression curve. So this is the coefficient of determination. The closer R squared gets to 1, the better the fit is. We are only going to do nonlinear regression using technology, and the example that we're going to look at here is a bacteria culture. So the first thing that you should do is create a scatter plot of the data using Desmos by copy and pasting the table. Try this to make sure that you're able to do it. I will link a separate screencast going over creating the regression lines using Desmos in our unit outline. Your scatter plot should look like this here. And then what we're going to do next is perform linear, quadratic, and exponential regressions. So the instructions are here for you. This one here is the linear regression. It is important that you use this symbol. That's what helps you to get the fit. And then it displays the coefficients for you. Okay. Desmos will also give you your coefficient of determination and correlation coefficient because we are trying to fit a line here. So our R value here is actually quite high, 0.91. But when we look at R squared, we can see that it only accounts for 83% change. So let's take a look at our next type of linear regression. So this is what you type into Desmos, just like above. Okay, make sure you have the subscripts for the ones. And this is going to generate a parabola or a quadratic. Our R squared value here is 0.993, a much better fit than our line. And the last one that we're going to see here is our exponential. So this is what you type into Desmos. It will spit out your statistics. And then here's our R squared value here. So 0.9965. This is our best fit or best regression for this table of values. So let's move on and answer some questions. For C, we're going to say our exponential is the best because the R squared value is closest to 1. And then what we're going to do is use our model to answer some questions. So I'm just going to write the model down here. So 8.946 y.795 to the x. And this is the whole reason behind regression. We want to be able to create a model so that we can make predictions about what's going to happen to this trend in the future or in the past in certain cases. So let's determine the initial population. So for the initial population, we are going to let x equal 0. Okay, and just to add on, y here is our population. And let's just double check with our table of values. X is going to be the time in hours. So at 0 hours at the beginning, we've got 8.946, 1.795 to the 0. This part of our equation is going to go to 1, and that means that we get our bacteria population is about 8.946 here, which we can round down to 8 for our population. So then if we go to create our next prediction, so after 18.5 hours, we would let X equal 18.5. Substitute in here, 1.795, 18.5. This is something you would evaluate on your calculator. $8.946 gives me 448,560. I'm rounding down because the information tells me that I've got a decimal. It hasn't quite gotten to the next cell of bacteria. So I've got approximately 448,560. And for my initial population, I've got approximately 8, rounding down for the same reason. That's an example of nonlinear regression. We chose the best model for the